Thank you, Panos. Good morning, everyone. Thank you for coming. So I'm going to cover the technological side of the project, which is a piece of the puzzle, it's not a complete puzzle. I'll describe a little bit of background, but I won't focus too much on that. We've covered that today, and we covered throughout today. A little bit about the technology. I won't go too deep into the physics of it all, but hopefully you'll come away with an understanding of how it works, more particularly perhaps how it differs from some other technologies you might want to try, to see what sort of space it's in terms of its potential application in this area, and where we are and where we're going. So, certainly in terms of scope, I mean, I'm not going to cover the background at all because we've heard it already. It's AVM. These are big things in the ground containing a lot of explosive. All of those things are important to the approach we're taking. Large, a lot of explosive in the ground. So if we look at the ground, and when I show this picture, it's not because I don't understand, it's a little more complex than that. But just the way to look at it, we're talking about a target in an environment. And that may be under the ground, certainly I'm mostly talking about that, but it may, for example, be on the ground in vegetation. There's a sense of, there's an area above that environment, which is usually where the sensor goes. So again, that may be vegetation, it may be the surface of the ground, that interface between air and environment, and there's a mine planted in it. So as I say, the sensor is usually above that environment. Again, vegetation, ground, whatever it is. And if it's an EM sensor, electromagnetic sensor, in broad terms, we have a signal going out and a signal coming back, and you're interpreting that signal, and that's your answer. And I've characterized these in terms of what that return signal is. And again, these are very broad strokes, but basically think of it as a reflected signal. It's the same signal coming back, but bounced off something. And that's GPR is an obvious one there, but there are also other methods as well, which people have tried. Acoustic isn't electromagnetic, but it's the same thing. It's a wave going out and coming back. Induced magnetic field, so you're inducing a magnetic field in the object, and in some sense, the antenna that you have and the object are then coupled together, and actually what you're monitoring at that point is the change in your equipment that this induced magnetic field has. And that's the basis of metal detection. It's really what you're monitoring, what's going on with your kit, to work out what's going on under the ground. Stimulated emission, the example I'm using in neutronic activation, that's where you send out one type of VM and you get a different type of VM back. So you may send out an X-ray and get a neutron back. You may send out a neutron and get an X-ray back. So you're shifting between the two. And what I call resonant retransmission of absorbed EM. So in other words, it's the same type of wave coming back, but in between it being sent out and coming back, it's been absorbed by some material and then retransmitted. There's a delay, and also it's resonant. It happens at a particular frequency. And I grouped these into two basic categories: anomaly detection and explosive detection. So anomaly detection, it's your basis of thinking this will detect the landmine is that the only thing in that environment which would give that signal would be a landmine. Not directly detecting the landmine, but something which is anomalous. It shouldn't really be there. Metal is an obvious example. In an environment where you don't expect to find metal, if you detect metal, maybe there's something there. So it's an anomaly. And explosive detection is fairly straightforward. You're directly detecting explosive. And by the way, I haven't put up the dogs, the olfactory test sensors, animals, and these electronic sniffers. I'm going to focus on explosive detection for bulk, and I'll talk about why. But in that sort of stage, it's the same sort of idea. You have the sensor above the environment, and it's actually detecting something coming out of the object. But it is explosive detection. So for the case we're talking about, where you have a large explosive charge in a cluttered environment, it does tend you towards the idea of explosive detection. Oops, the light going. So, in our early discussions with Halo Trust, it was on this basis. They basically, as Michael ably said this morning, gone through all these options and arrived at explosive detection for this very particular scenario as the right approach to take. And Michael explained why. I mean, cluttered environment, potentially issues with other things, mechanical appearance and so on, meaning that really you've got to look for something else, and the thing they came looking for was explosive detection. So I'm going to focus on a technology which is for explosive detection. As I'll explain, it's for bulk explosive detection, so it's not trace, it's not vapor or residue, it's the actual bulk explosive. And that is quadrupole resonance. Resonance itself is something you find in many areas of life, including at every party you've ever been to, someone playing on a wine glass. Here you're putting in effectively a broad range of frequencies, only one of which is absorbed, the resonant frequency. And so that clear tone you're getting back is because it's that object resonates at that frequency and only that frequency. So it's characteristic of the object. In these cases it's mechanical, so different levels of water in these glasses, different size of glass. The same excitation produces a different note based on resonance. So it's not like radar, where it's reflected, the same signal coming back just because it's reflected off an object. It has been absorbed, and then you get a frequency back. So in quadrupole resonance, we're transmitting radio frequencies. This is the range they're at. And that's important to us because that means, of course, it goes through opaque material, like ground, plastics, and so on. And there's an interaction at the nuclear level, which is what I call nuclear quadrupole resonance. I tend to leave nuclear off the front of my slides, not least because, you know, going through airports with something with nuclear written on it is not necessarily a great conversation you want to have, especially if you then say it's for detecting explosives. So those are two words which sort of pop up, which you don't want to put together. But it's in that nuclear level, there's an interaction. The EM is absorbed. If it's the right frequency for that particular compound, it's absorbed. And then once you stop pumping in energy, it wants to go back to its original state, and that energy is kicked back out again. And that's what you're detecting. When it goes back to its original state, which is the state it's happy to be in, it throws that energy back out at you. And as I say, it's at a characteristic frequency. And I mean, there's quite a full range of frequencies it potentially could be, but for the NQR, so for the nitrogen NQR you'll find in these explosives, it's going to be in the low megahertz region, 0 to 6 megahertz around. But you'll see these different explosives, these different blue lines correspond to different frequencies. So different frequencies and therefore different materials. So if you're looking for RDX, you'd be looking at a different part of the frequency spectrum than if you were looking for TNT. And if there was RDX present or TNT present, you'd expect a response at a given frequency. So if you excite across a range of frequencies and then switch off, if it pops up at a particular frequency, it's going to tell you something about what's there. So how does this work in practice? Well, you're basically, a bit like metal detection in this sense, these two have got to be magnetically connected. You are inducing a magnetic field in the sample. And indeed, that induced magnetic field is affecting your electronics. And in very early days of NQR, that's what people monitored. Just like metal detection, they detected the change in the coil, not the retransmitted signal. But there are many things which change the property of the coil. So in the early days in the lab, of course you just arranged that there was nothing else there which would change the properties of the coil. Therefore, if you changed the properties of the coil, you knew it was the thing you were examining. But out in the world, many things will affect the property of the coil. So you're back to being like an anomaly detector. But you don't want that, you want something specific. So rather than detecting the change in your electronics from that induced magnetic field, as I say, you switch off that magnetic field and listen for the energy coming back, which will be at a very specific frequency. But this induction, this coupling of the sample and the coil is key to how the approach works, because how that changes affects what you can do with the technology. So the three key characteristics are the size of the coil, the size of the sample, the target, and the distance between the two. And there's a critical interplay between those, which basically means that if the sample is very small, you're not going to detect it, even with a big coil, from very far away. So, for example, if you're looking for an AP mine, which is quite a small target, and you have 50 grams of explosive material inside, and it's, of course, the explosive we're looking at, not the physical size of the object, the physical size of the explosive within it, then even with a nice big antenna, as it gets further and further away, you've got much, much less chance of looking at it. But these three lines represent the size of the target. Again, I'm talking about the explosive content, not the physical mine. And what you see is, if you have a large target, even if it's a long way from your coil, you have a much better chance of detecting it, even if you have a small target really, really close to the coil. So this is why this technology is particularly suited for AVM. You're talking about an interplay between the depth you expect to find these mines, might talk about 5 to 20 centimetres, we also have to consider things like wheel ruts and so on, and the size of the target, which means you can create a system which can couple the two together, your system and the target, at the ranges you're interested in. And this is why, again, for this particular application, the technology we're discussing, quadrupole resonance, is suitable. Whereas for some other applications within the same scope, for example, AP mines at any sort of depth below the surface, it isn't necessarily still true. And in the past, a lot of the military exploration of this technology has been to look for AP mines and create systems to look for AP mines. But as I say, that's a small target. It doesn't couple well into your kit. So it's not the best case. Here we have a much more favourable case. The two can couple together very well, so the signals can be detected even at much deeper depths than in the case of AP. So it means that the system can actually work well in this particular scenario. So what does the system do? Essentially, it's a transmitter-receiver. Your phone is a transmitter-receiver of radio waves. We're working lower frequencies, but essentially it's a transmitter-receiver, just like your phone. So you have a way of generating the RF that you're going to use. You need to amplify that. You need to reach the target. And I'll show you a graph showing you how that falls off. But then the system we're using, which uses quite cheap electronics, and in the first instance, we simply switch on and off the RF at the frequency we're interested in. Remember, I'm talking about megahertz? So say 3 megahertz, we switch on and off at that sort of frequency. But by the time that reaches the actual antenna, that is then shaped into what's more traditionally thought of as an EM wave. It's called a sine wave. So it's been shaped by the actual hardware into that sort of shape. And that is then incident on a target. And again, if the target has a resonant frequency, which is included within that little basket of frequencies we've just excited it with, it will then, once we switch that energy off, return a signal. And you can see the signal there, you see the difference between the two. This has the signal you're sending out has constant amplitude, the signal you're coming back dies away. If you imagine ringing a bell, you strike it, you get a tone, and it dies away. It's exactly the same idea. But this is key to us as well, because that time as well, not just the frequency, but the time the signal takes to die away, is characteristic of the material. So now you have two orthogonal characteristics of the signal to latch onto when you're trying to decide if you've found your target. So the way you then determine if you've got it is the NPR signal is then boosted again into a slightly amplified again, I should say, into your receiver. You do some signal processing, and you usually decide if something's present or not. Classically, I should say, you determine if something's present or not if it's a signal larger than a certain number. I'll talk about, we don't necessarily use that approach in our project, but as classically, it's that sort of idea. It's the thing you're looking for popping up above the noise, essentially. So what that looks like in practice is our spectra are very straightforward. They do tend to be like a single line, and the spectra that goes, they're very boring. Certainly if you're a spectroscopist, they're very boring indeed, but it does make it simple to characterize. So that's all well and good. and if the material isn't present, that thing doesn't pop off at all, so you decide it's not present at all. So nothing detected. But if we look now at the case where, again, distance between the targets a little further, look at the difference in the speed at which the signals are growing. So on the bottom right, our signal's still growing, whereas on the top left, we've already decided we found it. And this is the fall off you have with distance. So this feeds into how you design the system. I say it's helped by the fact that you have a large sample. But if we look at that fall off as a graph, you have basically your field going down, and your signal's going down even quicker because you lose both signal from the fact that you have a weaker field exciting the signal, and then the signal itself's got further to come back, so it's weaker by the time it reaches your detector. And by this, I'm talking about not in the sense of broadcast, where broadcast radio, for example, obviously the further you are from the broadcast antenna, the weaker the signals get. I'm talking about that coupling between your system and the target. The further they are apart, the weaker that coupling. So what we're really looking at is the strength of that coupling, the induced magnetic fields. And as I say, that's for us is helped by the fact that the target is large. So when we build a system, all the dimensions end up being roughly the same. The target is around 20, 30 centimeters, whatever it is. The diameter, the radius of our antenna is 20, 30 centimeters. We're trying to find it down to a depth of, down to 20, 30 centimeters, depths in between that, but there. So all these distances being pretty much the same, which is very useful for us because it does mean that we can be sure that we're coupling into the target quite successfully, that we're going to be getting signal from it. The challenge is not getting signal, it's everything else. So this morning our speakers, when they opened the conference, they talked very much about being directly applicable to the communities we want to go into, and Michael talked about dual use, military dual use restrictions on using technology in this field. So one of the things we've looked at a lot is making sure we're not going to be doing things which ultimately someone will say, that's fantastic, we love that, so we're not going to let you take it anywhere. So we focused on making sure that our technology does the job it needs to do, but doesn't drift into dual use. Some of that is in simplicity, some of it is in the way we do it, which may not necessarily be the way we would do it for a military application, and making sure everything works on pretty dumb computers. So we've looked at size reduction, obviously durability, ruggedness, certainly detection, ease of use, and cost, but for the specific application. And then we have like a first shot at it, and then we take it out there and talk to our partners about how we can then make it specifically to work with their circumstances. And one of the things you may have seen from that picture is how crude this is. And you think, oh my God, that's really crude, that's embarrassing. No, it's deliberate. I mean, we've made this with copper pipe, and we've stuck it down with plastic. And this actually is a dustbin lid. This is deliberate. We don't want to make something which can only machined by a laser cutter to using high oxygen content copper etched to a particular design, and then it's so has to go into then a laser, a 3D printed or indeed molded sort of surround, which is all done in one location in the world. This is something which can be made anywhere, this part is made anywhere and indeed repaired anywhere. The rest of the kit, we went down from the commercial instrument which came from the USA, and indeed we have to sign bits of paper saying we're not going to take it to different parts of the world again when we buy it, to something which is very small and key, it's either bought off eBay or it's something we can make, and we can make open source. So anyone, anywhere can make their own circuit boards from our stuff. So you end up with a system which looks like this. So you have an antenna which is literally copper plumbing pipe and plastic cover. And I must admit, I am concerned about whether or not the value of copper goes up and down as to whether or not this thing would actually stay inside the cover. I'm a little concerned about that. But It can be replaced very quickly if that does become an issue. The transceiver electronics, which are bespoke, some of it's bespoke, some of it's designed specifically for the project, but it is open source. And commercial off-the-shelf stuff all from eBay. So a lot of it looks really crude, but that's, again, it's deliberate. It's one of the things we want to make sure that anyone can put this stuff together. And a tablet or laptop. Currently runs LabVIEW because it's a research environment, but it will run off an executable in Java in the future, and again, that will be open source. And then it works off a, well, it works off any 12-volt battery, but you know, we've tested it on just basically car batteries. And this system we've been trialing in UK currently, and we're going to take it out to Somaliland in June. We actually hope to take it out to Somaliland a lot earlier than this in the project, but well, you'll all be familiar with risk assessments and method statements, RAMs, and the RAMs on this turned out to be more complicated than we anticipated. It's a bit granular in the university, and the experiences in other parts of the university didn't necessarily reflect on what turned out to be our experience, but I'll take you through basically what happens when you take it out of the lab into the field, although bear in mind this is actually a quarry in Somerset right now, but again, this is all done with the understanding it's going to go to other places. So you've got a nice big antenna that you've made this size because you want it to be sensitive. Well, sensitive is great in some respects, and in some respects not so much, because if you take it outside of your nice lab, suddenly it's sensitive to all sorts of radio frequency interference. So this was just in our lab outside the RF shield, and most of that stuff is because we're in a lab with lots of electrical things plugged in. But if you take it out into the world, so this is outdoors in a trial site, and you'll see the site very shortly, and you'll see the noise is basically higher, but you get a lot of spikes of interference coming from, again, devices. Radio frequency interference coming from devices. So you've gone from, well, it's really obvious, that's the signal, that one thing that's present in the lab thing, to, well, I don't know, maybe not. So you have to be smart about how you determine what's really a signal and what's not. And so that's then the second element of the technical side of things, which is how one processes the signals. And we have a lot of expertise here, thanks to our telecoms group. Barbara mentioned this morning, our leading research in the wireless world, and so Panos is particular, Wakas is in the room as well, have been key to this. And we're looking, again, classically one looks at the idea of, can you see a signal above a certain level? This clearly is not going to be helpful here, so we've looked at other approaches. So we took our system out into a quarry in Somerset, and when they weren't blowing things up at the bottom of the quarry, we were at the top of the quarry in a sand pit and in a lab looking at, it happened to be military grade C4. Here at King's we do have a license to keep explosives, but it's very, very small. Well, post 9/11, so back to 2001, it went down from like 1.5 kilos to like 100 grams. So when we want to look at large amounts of explosives, and this is explosive detection, we do need to look at the actual explosive. We go to other sites, and as I say, right now that's a quarry in Somerset. And we looked again in the sand pit, again not necessarily reflecting what the actual environment is, although for the roads, perhaps closer than you would expect, and did some work on signal processing in a hut. So this is sorry about the laser prod, I can't remember how to get this to work correctly on the screen. But the, see if I can get that up. So we were working in this area of the site, and they were down at the bottom there blowing things up. Okay. So what we were seeing typically when we were over the target, not over the target, now as technical experts we could tell which one was which, but of course we're trying to create systems for use with non-technical experts. So we can't depend on people interpreting these two pictures and arriving at a different indication that there's a target present, target not present. In particular, you'll see that there's a source of interference which is really close to what the actual line was. So this on the right is our frequency, our spectrum from the target, which was C4 as I say, and the one on the right is some sorts of interference. So we have to come up with a way which will process this information, arrive at a determination which doesn't rely on interpretation by technical experts, but is rigorous enough to cope with environments where you have a lot of interference. Say classically one would use a thresholding approach. Is the signal bigger than anything else? But what we've gone for is machine learning. So this allows us two things. One is the simplicity. Basically, it'll do it without needing a technical expert to interpret. The other is it can work with very noisy data, so it can actually work more quickly. And machine learning, sometimes you may think of it as an AI, artificial intelligence. Sometimes it's called data science. Basically, it's crunching numbers. And if you're smart about it, it will come up with the right interpretation based on those numbers. And the particular aspect of machine learning is that, in essence, you don't know how it arrives at decisions. So you've got to teach it what's right and what's wrong, and then test to make sure it makes the right decisions. And of course, teaching people what's right and what's wrong is one of the toughest things to do. So the way we're using it is a support vector machine. It's just one particular type of approach. The reason we use it is because it lends itself very well to what we call a binary classification, a yes or a no. And in explosive detection, that's what you want, yes or no, present or not present. The different approaches are the two diagrams represent either linear classification, you draw a line between sets of points, or non-linear, which involves a little more work and a little more design. And in a non-linear problem, which is what we have, our signal doesn't behave in a linear fashion. You do need to go into design and you have to apply what's called a kernel. But again, that's part of the design choice, and a lot of the work goes into the particular kernel you pick, which turns a non-linear into effectively a linear binary classification. And so you train it. You basically, it's called what's called a supervised learning. There's supervised and non-supervised. And in supervised, you tell it. Some of the training examples are one class. Those other training examples are the other class. And you tell it which ones are which. And that's your training set. And then you basically, once it's trained, you give it further examples and let it sort them into the two classes itself. And you determine how well it's gone by your knowledge of what the further examples are, and you assess its performance based on that. Challenges with SVM, or indeed any machine learning, is the training data. It basically, again, you've got to teach it the right way. And I've talked that this problem space may lend itself to regression rather than classification. Well, here we have samples which are maybe further away or closer to our antenna. Then we can't cover every distance. We can't cover every orientation of sample in our training data. So it needs to be smart about something not quite the same as what it's seen before, still being a target or not a target. And regression allows you that fuzziness, where basically it's like adding a threshold to the classification. So, but again, that requires a good training set. So in the lab, where we can control the training set quite well, and we can actually generate large training sets. If you look at the blue and the red, which represents just two different ways of treating the data for the machine learning, and the brown and the black, which is that thresholding approach you saw in the earlier picture, the classical approach, that and the number of accumulations, which represents the signal to noise in this instance. Basically, the SVM doesn't really care whether it sees noisy data or not noisy data, whereas the classical approach definitely needs to have data which is not noisy. So the level at which the classical approach approaches the performance of the SVM only happens when you've literally got 1,000 times more bits of data. So this is additive. So basically the signal is 1,000 times stronger added up. The noise has gone up by root of 1,000, basically, in terms of signal to noise. So this is the potential of the machine learning, but key is the training set. So if we look at what we're doing now, and this again relates to going to Somaliland as well, it's generating our training sets. And that involves going back to Somerset periodically and getting more and more data and throwing more and more scenarios into the mix. It's still supervised learning. We're still telling it which is in the training set, which is has a target present and which doesn't. But again, the test is always to then throw in examples where it isn't told and letting it tell us what's happening. But one thing that's come out of these trials going to Somerset is we do need to work on our ruggedness. I mean, we took 2 systems to Somerset the last time, and only one of them actually worked. The other one broke in transit. And even though we took lots of spare parts, the thing that broke was the thing we didn't have the spare of. This is typical in these situations. So we do definitely need to work on the ruggedness of the system. Again, not sacrificing its simplicity and ease of maintenance, but building in ruggedness. And we need to automate. So these 2 gentlemen here are ex-EOD operatives employed by the company that runs the site in Somerset. And all they had to do for the day, literally all day, was sit and stare at our people, stand and stare at our people doing the experiments. Because right now, the system requires a technical person to run it. So we need to get them out of standing by the side of the sandpit into the sandpit. And that's the final element of the work we still need to do. But part and parcel of that is these trials we're running in different locations where we talk to these EOD people about what would work for them in terms of what they need to see and be able to do. So we don't want to automate until we've had those conversations with a full set of trials. So that's the end of the technical presentation. We've come a long way in terms of making sure we can detect the signals reliably in the situations you want to detect the signals. Now, as I say, it's about this thing about putting it into the hands of people who need it. And that's the stage we're at now. We would like to be a bit there earlier again. The RAMs on that turned out to be very difficult. But we are there now, and that's the next step. Basically turning it from a piece of kit which works really well in our hands into a piece of kit which will work well in the hands of people who need to use it. So thank you for your attention. I'll take questions, and of course I'm here for the rest of the day.
Thank you very much, Amy. Questions?
Hi, hello. Just wanted to ask, can you use the device from a moving vehicle, or do you need to be stationary above the target? And if you need to be stationary, for how long?
You need to be stationary. For how long will depend ultimately on how well we can train the system. The system we have right now takes like 2 minutes to look at a distant mine, but we don't have a full training set, so we don't have that optimized. It's not a quick technique, and in a sense that's to our advantage, only in the, well, in one sense it is. And that's in the sense that it isn't military dual use because it's too slow. These type of explosive detection would be very difficult to use for maritime use if it could actually work in the military sphere. So yeah, it sits over the target for a while, but that does give you definite explosive detection, not anomaly detection, explosive detection. Content, mine content detection.
And angle of penetration, does it have to be straight down? Or can
No. The field is radial. So
Right.
basically it's a sphere of RF going out, and the signal's coming back, you know, any angle onto that sphere. So basically it doesn't need to be a particular angle to the coil. This is very key to us because, again, my simple picture of a block and a block doesn't represent what we know we encounter. That thing, the target could be at any angle with respect to the antenna. What matters is that for us is it's large, and our antenna is the same sort of size, so the two can couple together despite that orientation. Michael's talked about uneven road surfaces. He's talked about wheel ruts and so on. We really won't know what the relative orientation of the two will be.
Right. So I know that this is still in terms of the experimental phase, right? So one of the question was, how do you determine the size of the coil in terms of the sample size? Because there's a trade-off in sensitivity when you are making the coil.
Ideally, and I mean this is why this sort of works well with this particular application, ideally you want your coil to be about the size of the sample, the target. So if you're talking about a disc of, say, 20 to 30 centimeters in diameter, you want to start with your coil kind of that sort of size. If it needs to then look further away than, say, 20 centimeters, which it may need to do, make it a bit bigger. But then don't just keep making it bigger because of the sensitivity issue in terms of you're introducing a larger problem in terms of RF. So basically you end up with a coil which is a bit bigger than the sample and kind of the same sort of size as the separation between the sample and the coil. I say in this sort of instance it happened to be that these things are like the same sort of numbers. The target is the size of the separation and then you can work with the coil pretty much the same size. Again, the AP problem, which was the military research into using this technology, these things weren't the same numbers. The target was very small, smaller than the potential separation between it and the antenna. So the antenna got bigger, but the target never got bigger, so the coupling between the two never improved. But it was hard to improve it past the point where you could get it deep enough, but still actually couple into the target.
Right, follow on to that answer, maybe just a quick question again. Like let's say, if you're talking about the size of the coil, right? Let's say you talked about 20 centimeter. So, I mean, how do you detect over a larger field? Because this is in an open field. So, I understand that this is still in the experimental phase and you're scanning it through.
Oh, you'd have to move it. But I mean, one of the things you can do, and one of the things we're looking at, I should have said this actually, is you don't need to have one of these going. You can have more than one of these going. And there's a smart bit, which is the computer bit, which again we still want to make dumb, but smart-ish. And there's just the RF bit, which is the plastic bin lid with copper pipe inside. And so you can have more of those going at once. You can cover a larger area. And if the smart bit is running more than one system, it can even interweave so they don't interfere with each other. So you get gains from having a multiplicity of systems.
Yeah, my question actually was like, in terms of monitoring, have you thought about making it autonomous, like using drones or something, so that active part could be removed and it could be made passive? We could remove the 12-volt battery or something?
Okay, I should say where I come back from originally. I'm part of a robotics research group. And there was a lot of interest in parts of the world in using robots in this. But I don't. I use plastic and copper. Why? Because robots cost a lot of money. And it's not been made clear, certainly to me, that it's technically feasible to do this, but I don't see it at a cost where at a cost where it will work for humanitarian. The second thing is, and this is always the issue with autonomy, at the end of the day, someone has got to drive over that road, and if the only thing that's been there before is a robot or a drone, I mean, again, you talked about perception. Have you really cleared a location if people still perceive it to be mined? I mean, you take them all away, they're gone. No, the perception's there, in which case you kind of haven't cleared the location. So, technically feasible? Absolutely. What you want to do, I'm not convinced. And I say that as someone who works in a robotics research group where it's my job to find applications for robots. And then I don't spend all my days not doing that.
Thanks. I'm not sure I understood that much of what you said, because it was but it was very interesting. I could see lots and lots and lots of applications for this. I've spent 25 years clearing bombs, and there are many different ways that this could be used, and far more than just anti-tank mines. But I think it would be understanding, because obviously you've just touched on, trying to cover so many different things here. But thinking of something like, we're talking about anti-tank mines. Anti-tank mines are pretty straightforward in that they've got a case and they generally have a pretty consistent explosive mix. how will you, would this be able to pick up on HME? You know, so if it's homemade explosives made in from different fertilizers with different components, different mixes, different precursors, is it still able to pick up on the characteristics of that, or would you have a wider RF range, or the sensors need to be more sensitive, or how would you deal with a non-standard mix of explosives?
The short answer is time. You'd spend longer about it. You basically, because effectively what you'd have to do, it's a resonant technique. So you're looking for a signal of a particular frequency. If you then, and for our application, we're looking for like one explosive, RDX, or potentially TNT as a second. If you then say the threat set is N, where N is an unknown number, then basically you're looking through that threat set and it just goes on and on and on in terms of time. If you could limit the threat set, and again, if your threat set is 1, the certainty is greater, the time's less. So we've looked at, the very first project I worked on in this area was CANS, calcium ammonium nitrate sugar, improvised explosive used by PIRA, provisional IRA, in the good old days. And that was basically just ammonium nitrate. And that's what we were looking for, that's what we were targeting. And then we started looking at other improvised explosives. As more and more actors came into this field, urea became a thing. We never thought urea would be a thing. In fact, there's so many improvised explosives we never thought would be a thing that are now a thing. And you just keep building your threat set. But every time you add something to your threat set, you've increased your time effectively by n, power to the power of n, because you have to change something, then look, change something, then look. So yes, there are many threats we could look at, scenarios we could look at, but is it realistic that we'd be able to do it in a time people would be willing to spend waiting for that? And the reason we focused on this as being particularly suited to what we're doing is because of the well-defined threat set. Target, distance, size, environment, all these things play in our favour. So again, the military tried developing this technology for many years, but their threat set just kept growing. So it never went anywhere because ultimately, there wasn't the time to look at all potential threats.
Is that also computing power?
It's not just computing power. I mean, it's very difficult to excite a broad enough frequency range to cover everything in one shot. So you end up stepping through things. Sorry, yeah. You end up stepping through things.
That's exactly what I was implying. I'm not sure I understand the physics of it, but I can see the use of it. In terms of distance, you say, what would be the range if you were looking for, say, a target that was 20 kilos rather than 5 kilos? Could you then be doing a standoff of 1 meter or 5 meters? Or how would that work in terms of a bigger distance, bigger target?
Provided you could basically configure an antenna which would get close enough. And one of these things, again, about the size, which works for us, is even with rugged terrain, you still start being able to get it to where it needs to be. If you start increasing the antenna to get further away, you're reducing the number of places that antenna can go. So if we were looking at 1 meter, I might want to be looking at a 2 meter antenna. And Michael in his slide showed you that big metal detector rig, which was great for a road, but wouldn't necessarily work for a path, wouldn't necessarily work for if you're trying to get through doors of buildings, and so on. So yes, you could go up in size if the target was larger. You go further away if the target was larger, but you'd then have to go up in size in terms of the antenna if you want to look further away, and it would still cut into the target, but you'd limit the number of scenarios where you could actually get one on top of the other.
Just we're dealing with a lot of IEDs at the side of roads, so they're not they're not on the road, but they're big enough. So they're using the P for plenty principle that you have 25 to 50 kilos of explosives further away, but it then blows the vehicle off the road.
Yeah.
So I'm just trying to understand, because as I say, I see there's a lot of potential for this.
Well, yeah, I mean that's potential. To be clear, this is RF, so we are talking minimum metal still. So your metal detection is still your best bet for anything which is bulk metal. So getting RF into largely metal objects is tricky, although the CAN scenario I described was actually inside vehicles. But, it's not a scenario you want to encounter if you don't need to.
So if it's in a metal casing, the metal casing will affect the frequency?
Oh, no, metal casing will affect your ability to get the RF inside. Sorry, I should have said that. I mean, this is specifically the minimal method scenario that Michael described. So it's specifically for that threat. As I say, the attenuation of the RF going in and out.
A lot of the IDs we're dealing with are in palm oil containers anyway, so they're not metal crates.
Yeah. As I say, I mean, I was looking for cans inside boots, back of vans, and so on. So, you know, it can happen. But as I say, the number of scenarios where you did counter it, although the scenario decide probably would be okay.
And in terms of time, I mean, to process, let's say, a suitcase, what would you be saying? 2 minutes, 5 minutes to process a, you know, if somebody brought a suitcase to an entrance and you wanted to check it, what would be the processing time for that?
Again, depends on the threat set.
Right.
I can't say beyond that. I mean, I could say take 10 seconds, but if the threat set was too large, you might as well say an hour. I mean, you know, it depends on the threat set.
If you're stopping it going on a plane, it's maybe worth it for an hour.
Yeah, and then you say that to people, and in airports, and then they say, no, you've got 6 seconds.
That's when they're civilians.
Yeah, that's right.
There was one last question.
My name's Chris, I'm from the Halo Trust. I think most of my questions have been answered by the discussions that have followed afterwards, but just one back on drones, if I may, and this probably links to timing. If you're using a drone deployed detector, then it's great possibly on a minefield that you would expect to be a flat surface, football pitch type. But the deployment of drones, particularly if there's vegetation, high winds, etc., that makes drone deployment quite difficult. And if it's got to hover above a target for any period of time, then that effectively rules out the use of drones. And also there's this question of perception as well, where people say, well, great, you've put a machine across it that's been flying. Would you walk on it? My answer would be no. But anyway, that's my point on that.
But I mean, I know people and you probably know the same people myself, who wouldn't walk past a field which would be mechanically cleared. So, you know, I mean, perception is a big, big deal. In the robotics group, we're working on getting drones to hover. I mean, again, there's a lot of work on control. Barbara mentioned the control group we have here, where you can actually now, these days, even quite strong winds, get drones to hover quite well. But yeah, I mean, great. It'll cost a fortune, and someone still has to walk across it at the end of the day. Yeah.
Okay, thank you very much again. And